So this is how we can write down any differential n form as well, but for now we will mostly focus on differential 2 forms and differential 3 forms. So let me get to another page. Okay, so again, these differential forms, even you go for n form, they will also give you some determinant and stuff. So let's take an easy example to see whether we have actually understood the idea behind these differential forms or not. So let's consider an example where, so this is an example. Let's say I have two vectors, b given by 1 2 3 and w given by 4 5 6, and we want to find out what is dx1 wedge dx2 when this is acting on v and w, right? So if we recall the discussion we just had a few minutes ago, this is just dx1v, dx1w, dx2v, and dx2w. And this is just what? This is just 1. This is 4. This is 2. And this is just 5. So this means this is just 5 minus 8, which is equals to minus 3. Okay? And what if I tell you to calculate dx1 wedge dx1? Would you go with this method? Obviously you can, and you will see that the result is 0. But there is a very straightforward way of seeing that. Recall from the antisymmetry property that if I exchange these two, that means 2 goes to 1 and 1 goes to 2, we pick up a minus sign, right? So similarly, using this property, I can write dx1 wedge dx1 is equals to minus dx1 wedge dx1. And these are the same thing. And they are equal and opposite to each other. So that means dx1 wedge dx1 must be 0. So this is another useful property that will help us a lot in future. And similarly, you can do things for differential 3 forms and all that. Now, since we are almost done, we want to show some properties of differential n forms, that is some algebraic properties. We will not go into the proofs, but we'll just state them here for the completeness of this lecture. So algebraic properties of differential forms, and this will hold for any differential form, that means 1 form, 2 forms, L forms, whatever. So let's say omega 1 and omega 2, all of these are k forms. That means there are differential k forms. There are, if you want to count it in a novice way, there are k amounts of d. That means d k times. Okay, this is one way to think of it. And eta 1, eta 2, and eta 3 are L forms. Then the following properties hold. The first one is that a omega, that means this a is a scalar, a belongs to real number, a times omega, where omega is a k form, wedged with eta will simply give you a times omega wedged with eta, and this is also equals to omega wedge a eta. The second one is a linear property, omega 1 plus omega 2 wedged with eta would be simply equals to omega 1 wedged with eta, omega 2 wedged with eta. The third property is that if you have omega, this is wedged with eta 1 plus eta 2. This will give you omega wedged with eta 1, omega wedged with eta 2. And the fourth one is that omega wedged with eta is equals to minus 1 to the power k times L, eta wedged with omega. And this is a very interesting one. All of these are, but this one is the proof of this one is a little bit interesting. So we are not going to prove it, but this will help us in the long run when we are dealing algebra that involves manipulations of different differential forms. We will try to see that whether we can actually make use of these properties, and in fact we will. They will help us in computing different quantities that comes with differential forms. So now what we want to do is that, let's say you are taking let's say you are taking two forms, two differential forms. One is a k form, another is a L form. Okay, so let's say alpha is a k form, which can be written as alpha equals to summation of I ai dxi, like this. Again, this is a k form, right? So don't get deceived by this dxi over here. All of this will have k elements, and then there will be a summation. Okay, so this all of this dxi written will be are actually something like this: dx1 dx2 dxk, like this. And then the coefficients are summed over with this differential k forms. So this is one way to simplifying your notation. And if you have a beta, which is a L form, which can even be written as sum over, let's say, j, and let's say this is bj dxj, then alpha wedged beta will be just sum over ij aibj dxi wedge dxj, something like this. So that's the reason we are calling it simplifying, because all of these dxi capital I and dx capital J will contain actually k and L forms respectively. That means there are more dx's inside those things. And the last topic for today is the interior product of our differential form. Obviously, before we go into that, we can try to talk about the general formula of the Wedge products, but we won't go into the proof because there is another related product that is called a tensor product, and from that point of view the proof becomes easier. So I'll just write this formula for now, that the general formula for wedge producting different differential forms. So this is a general formula. If you have some alpha and beta, though that are acting 1v1 v2 vk plus L vectors, this is written as k factorial L factorial, and there is a sign of the summation, and there is a sign thing that actually comes from the totally antisymmetric tensor. Again, I'm not using this, though this is the most straightforward thing, because we are not discussing tensor, so that's why I'm not going to use it. And the sigma will belongs to k plus L. For different k's and L, you have to see what is the sign. Then you have this alpha, that is the differential form which will act upon these vectors, which is again just taking the projections times beta d of sigma. It should be starting from k plus l, that means this index, sorry, k plus 1, not k plus l, that should be the last one, and beta will act on this v sigma k plus 1, v sigma k plus 2, dot 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 of v sigma k plus l. This formula is totally optional. As you can see, it gets very messy. However, if you can use this Levi-Civita symbol, it becomes pretty straightforward. And now to move on to the interior product. This is the last thing for today, the interior product or the inner product of differential forms. So what do we mean by the interior product or the inner product? So as you can already guess from the name that it's kind of similar to the dot product, that because we have been saying this interior product is kind of similar to a dot product where you take some stuff, you do something and you get some number, right? But it turns out that when you take different interior products of differential form, it's not necessarily the same thing. So that's why I would like to call it the interior product, so that we don't get confused with the inner product of the things that we see in the vector space. So let's say we have a k form alpha. So let's say alpha, and sometimes we can even denote a k form like this: alpha belongs to capital lambda k. That would mean this is a k form on some manifold r to the power n. This is another way to express it. So this alpha is a k form, and given a vector v, let's say v is a vector, so the interior product is denoted with this dv according to the textbook that we are following. In fact, you can choose any other notation you want. So this is the symbol for denoting this interior product, and this interior product is defined as follows. So this is the interior product between a vector and a differential form. Okay, and this v1, v2, da da da, vk minus 1, they are just k minus 1 vector. And what this interior product does is that this tv alpha, which acts on these vectors, it just puts the vector v into alpha's first slot. Okay, so what does that mean? Because we are considering a inner product, sorry, the interior product between this alpha and this b, right? And we are only interested a product between in between them. So notice what happens in this definition. Alpha is a differential form, so eventually it will act on some vector, right? And those vectors are written as v1, v2, v3, dot dot dot, v of k minus 1. Now when we are saying that, okay, I want an interior product with respect to v, which I denoted with t of v, t underscore v, then what it does is that it gets rid of this v1, that means the dummy vector that was there, and it puts that v on the first slot. Okay, or you can think of it as it just creates a new slot and puts v inside it. So whatever is happening over here, it really doesn't matter. All this v1 v2, they don't really matter, and we'll see why this is so in a example. So let's take a very simple example. Let's say, okay, what do we want to do? What is the most simple one? A two form, right? If you want to take an example, the first thing would be to go for is a two form only. So this is a simple example. Let's say our differential form is a two form, which is denoted with, let's say, dx wedge dz, something like this, and v is equals to let's say v1 v2 v3. This is the v. So we want to compute this quantity. Sorry, it should be z. And since this is a two form, how many diamond vectors there should be? v1 v2. Okay, let's not call them v1 v2, let's call them w. Otherwise you might get confused with this v1 v2 v3 over here. Since by the definition it should do the following. It will put v and then will be w1 w2 like this, right? But face the fact, we don't have any clue about w1 and w2. We only know what is v. So how we write this is the following. So instead of this w1 and w2, we just put a dot over here. That means these slots are empty. We don't know about them. So this is written as dx dz v comma dot. And what it does is that if you consider how these two forms were defined, when they act upon vectors, they give you a determinant like this, dx v dx dot dz v and dz dot. It is defined as, since there is nothing to act upon these operators, that means the differential forms remain intact. So dx dot is just dx, dz dot is just dz, like this, and then dxv is just v1, dzv is just v3, and this is dx, this is dz. Now you compute the determinant and there you go. So as you can see that this interior product actually turned a two form into a one form. And we'll have to say something more about this type of things, where you can make a two form into a three form, and let's say three form into a four form, or you can convert a four form into a zero form in a 4D space. We'll have to say more about these things in the future lectures where we will discuss Hodge operators and exterior differentiation and stuff. So this is how you compute it. Pretty simple. Now similarly you can go for if you want to take interior products of three forms, you can similarly go this way. But before I finish off, I want to again consider some or show you some algebraic properties that comes from the definition of it, the definition of the interior product. So again, these are some algebraic properties of interior product. So the first one is that dv of alpha plus beta, again where alpha or beta are k forms. So alpha comma beta belongs to lambda k in the manifold of this. Okay, so this is dv of alpha, dv of beta. You can show this easily using the definition. Similarly, if you take two vectors instead of just v and you add them up, let's say v plus w, now you are considering two vectors and you want to find this quantity, this interior product. This will just be d of v alpha, d of w alpha, like this. Okay, and there is another property That is, if you want to compute the interior product to a differential form where your alpha and betas now are k and q forms respectively. So this is the case where your alpha and betas, where alpha belongs to lambda k like this and beta belongs to, let's say, lambda q. If you want to compute a quantity like this will turn out to be dv of alpha wedged with the beta plus there is a minus 1 to the power k alpha wedged with the dv of beta. So these are some algebraic properties, and a final one is a little bit interesting, which kind of looks like an anti-commutator if you are familiar with linear algebra, and if you are not, just take this property and try to prove it. Is that tu dv plus dv tu alpha, where alpha is again a k form, is equals to 0. And this thing kind of looks like an anti-commutator. So this thing is similar to an anti-commutator. And yes, this will be it for today. Even though you might think that okay, these are not pretty big deals, but when we try to do these exterior derivatives and Hodge-star operations, you will begin to understand why we want to bother with these algebraic properties and all these stuff that we have done in this lecture. So this is it, and thank you.